So after watching that video in regard to virtual memory and physical memory and how they work together, that you could have gotten it from your CD-ROM, we need to talk about the benefits of virtual memory address space. Was it really beneficial to us to use that? Well, virtual memory system helped us in order to make our application robust. We didn't have to be worried about memory management, if you remember. Operating system assigned us a 2 gig address space, and then we just needed to write our code. We didn't have to be worried about what portion of physical memory, is occupied or what portion is free. So that saved us a little bit of time. Also gave us a way that we could look at the memory in a flat way. In other words, we had a contiguous space from our perspective, but in operating system perspective, they were doing the complicated task of mapping it to the actual physical memory. In regard to threads and multitasking, I have another section in here. Earlier I mentioned that the definition of a thread was the smallest unit of execution and work. Now, as I mentioned, the more threads you have, the faster and sooner your application gets terminated. However, sometimes between threads, basically you're using the same threads. So, using the same resource. So for that, you need to synchronize between threads. You need to make sure that they are not overriding each other's work. So perhaps if you have a resource like let's say variable like X, if thread A is writing to it, thread B is writing to it as well, you want to make sure that thread A read back the value that is expected to be read, not necessarily something that someone else has changed it. So for those, we need to actually do protection, synchronization, and so forth. So we're going to talk about them later on. But basically, multitasking concept is running more than one thread at the same time. Think about this analogy. I ask every single student in my class to write her or his name, perhaps, on a piece of paper. And at the same time, I expect them to finish it at the same time. But guess what? Every single person has a paper in front of it, but you don't have a pen. I share the pen with you. In other words, I give the pen to you. I want you to write your name, and at the same time, I want everybody else to finish it. How is it possible? Imagine I'm a Superman. I get the pen out of your hand. You write your first character, get the pen away, give it to you. You write your first character, get the pen away from you, give it to the third person, and so forth. And I rotate this so fast that almost all the process is running at the same time. So that's the multitasking that is happening inside of the operating system. Well, basically, that's the speed of the CPU. And somehow I have to share the time between you and the pen that you have. In other words, I give you a time slice. I say you have 2 seconds. Then your time is up. I give it 2 seconds to another person and 2 seconds to another person. As you know, in this world, everything is about connection. You might be connected to me somehow, and I give you more time slice, or I take care of you first, sooner than anybody else. You know how it goes. So they call it thread priority. In CPU is the same thing. You could make one thread to run sooner or quicker than other threads, or you could have, again, perhaps more money and do more things in this planet. The same story in operating system is true. You could have a higher priority than other threads. You could interrupt lower thread priorities and say, hey, I have to be done first because I'm important. If you think about operating system, there are some threads that are pretty important. Well, think about them. The operating system threads itself. Operating system should be executing before you execute anything else. In real life analogy again, the police car or ambulance, perhaps, they have higher priority than our car by the time you're driving. When they, put the siren on, you have to stop. That's the whole thing. The reality in operating system is the same story. If a higher thread priority comes and asks you to stop, you have to stop. So that's the anatomy of thread and multitasking in operating system. So higher thread priorities can interrupt lower thread priorities, and of course, you have time slices and so forth. Well, as you see in this section, it's talking about multitasking, which is the ability of an operating system to give the appearance of simultaneous running of multi-thread environment. Again, is talking about give you the appearance of the simultaneous execution. But in reality, you only execute one task at a time, if you remember. But since you do it so quick, since the time slice is so little, you as an end user don't realize the gap between them. So all of them are really operational because the operating system runs a lot quicker than we can imagine. We can, you know, feel it. So is basically the time that you get the delay is tens of millions of seconds. So you really don't feel it. And basically, anytime that the thread switches its context to another thread, in other words, you give your time to another thread. Okay, I'm done. Now you can get executed. They call it context switching. Now this process called context switching and is done as follows. Running a thread until the thread's time slot is exhausted or until the thread must wait for a resource. Think about this. Imagine that I have 4 threads running. Thread A, B, C, and D. Thread A has 2 milliseconds to execute. Okay? You finish it after 2 milliseconds, you give your time to thread B. And then thread B runs 2 milliseconds, it reaches to 1 millisecond, but is waiting for a resource that is locked. Well, you have 2 choices if you think about it, part of design. The first is you waste that 1 millisecond and wait, keep waiting, and then your time is up. You got frozen, you give your time to another thread, and then by the time next time you come back up, you start checking if my resource is available yet. No? Okay, I have to wait again. Or you can design your thread to realize that your resource is available or not. If it is available, use it. If it is not available, you actually voluntarily give your time away back to the operating system. Say, hey, I have to still wait. I pass. Right? They call it preemptive multitasking. In other words, the thread itself is smart enough to understand that I have to wait, so I'm not going to waste everybody else's time. You can use my time, you can go ahead of in front of me. So that's how operating system 32-bit got designed. And then of course you save the thread's context somehow, because by the time you got frozen, you have to save the context somewhere. Persistence, we talked about it into the introduction. You don't write these things, operating system has done it for you. They are saving the state into the registers of CPU, so they exactly understand how to treat, your execution next time that your time slice comes. And then of course you could load another thread's context and repeat this sequence as long as the threads are waiting to execute. Let's take a look at this illustration in here. As you see, I have 2 threads, and thread 1 and thread 2, you can actually refer to page 4 on module 1 on your book 1011. And as you see, thread 1 is running its time and then gives its time away to thread 2, and thread 2 actually gets executed, and then thread 1 executes a portion of its time, as you see, but it waits perhaps for its resource, and then thread 2 is running, and then it gives the time back to thread 1 and then continues. So as you see, they call this switching context switching. You switch the context from one to other. In other words, a specific thread execution is going to almost be finished at the same time. As you see, the line that indicates done is very close. They're very close to each other. Another thing I have to tell you that here is not being discussed is a concept of inversion handling. Inversion handling is a concept in which you're running 2-3 threads at the same time. However, thread A, thread B, and thread C perhaps running. Thread A has the highest priority. In other words, it has to be executed more than anybody else, right? And then thread C is the lowest priority. Consider this scenario. Imagine it in your brain. That thread A is running, gives its time to thread C. Thread C time comes. Thread C uses a resource and puts a lock on it, but is slow in comparison with thread A. Thread A time comes, wants to use it. He says, oops, the resource is locked. Who is using it? The slow driver in front of it. And instead of hanging it, what it does is say, hey buddy, come and use my time. In other words, boost the thread priority of thread C in its own priority. It says, come and use my time slice, right? Gives away its time. And then thread C uses its priority faster, finishes it, releases the resource, goes back to its own normal priority, and then thread A takes over and continues. In other words, the operating system got designed like that. They call it inversion handling. It's good for an application, is not good for real-time programming. So we discuss these things in other courses like embedded courses. If you have more than one thread, that uses the same priority, which one will run first? Well, operating system uses a round-robin process. And if you're not familiar with the round-robin process, consider this scenario. Imagine you have like 5 different pens, and all of them have the same color, black. And you want to really use them all at the same time, or use them, in the same number of time, let's say. So you number them, perhaps thread 1, thread 2, thread 3, thread 4, thread 5, or pen 1, 2, 3, 4, 5. The way you use it, you put them in a list, in an order list. First time you use 1, you finish your time slice, you put 1, you put it at the end of the list. Next time you will use 2. In other words, you try to do the balancing between them. They call them round-robin process. So the first one got used goes to the last of the list, and then the second one comes first, and so forth. So they call it round-robin process. If you have threads that they have the same exact priority, well, that's how they are being executed. As far as the thread messages and message queue, there is a relationship between them. Before I talk about the detail of it, I'd like to explain messages. What is a message? We're not talking about emails or anything. It's just a matter of a notification from one portion of the application to other portion. Or perhaps a message comes from the operating system to your application. Or vice versa, from your application to the operating system. Let's put them into analogy. I move my mouse. What do? I move a hardware, and I ask the operating system to draw a pointer for me, and based on my movement, moves the coordination of that drawing. If you have been doing Windows operating system programming a long time ago, we used to design all the pointers and tell them how to move it around and so forth. Now you don't have to do none of those, because Microsoft provides that infrastructure to you. They say focus on what you want to do. You don't have to start from scratch. So what do? I send my window messages to my application, and I basically redraw my pointer right in here. Vice versa. I click on a minimize button of my application, and I ask my Windows operating system to minimize my window. That's how it works. So you see, it's a two-way communication. Windows operating system sends a message to your application, or from your application you send a message to operating system and say what to do. Anytime I click close, basically I command my operating system to get rid of my process. Or anytime I double click on this, basically I launch my application and I ask the application to go read this state, last state that was executing. So you see, it's a two-way communication. Or keyboard punching and all. So these are messages that are moving back and forth. In order to demonstrate the messages, I like to show you a SPY++ for a second. There's a utility part of your Visual Studio 6.0, and under Enterprise Tools, part of Visual Studio Tools, there is a utility called a SPY++. I don't want to get into the detail of this at the moment, but I'd like to show only a portion of it to you. As you see, the SPY++, it shows many different things to me. These are available processes that are running, and on each process there are sub-processes perhaps, as you see. In order to demonstrate this, I'd like to show an application such as Notepad. An application like Notepad is being discussed in here. What I'd like to do, I'd like to demonstrate this in a way that you can see both windows, so you can relate to it better. Okay, now if I click on Find, I have a choice to choose between properties or messages. I rather choose messages because that's the topic at the moment. Every single window that gets created has its own ID. Like you that have a social security number perhaps, or national ID, or a driver license, that you automatically become uniquely identified by government. The same story is true. Every single window that resides on the memory has to be identified. Column window handle, in other words, they give you a handle or a number which is uniquely identifying you. And not necessarily the same window gets open, has the same exact handle. I'm going to show that to you. Look, this is a target. I drag it over, and as you see, my document has a handle. As you see in your left hand side, right in this section, in this handle, you see the number, hexadecimal value. If I move it around, you see the window has its own handle, the document has its own handle. As a matter of fact, my classroom view has its own handle, operating system has its own handle, the time has its own handle. See the variety of different things, everybody has its own handle. Let's take a look at notepad window. You see, that is a handle, 0090162. I close my notepad and I'll reopen it. If I drag it over again, I got a totally different handle this time. So the handle randomly gets generated at that time. So there is no guarantee you're going to get the same handle. As long as you're running, that's your handle. So you can basically do anything with it. As a C++ programmer, you get a handle of somebody, you can almost handle it in any way you want. That's what they call it, handle. So I want to handle only this section, not the entire window, only this section, just the document. That's my handle, which is the edit, the class edit, or the class notepad. You see that? Now, I want to see all the messages. I'm a spy. I like to see what's going on. So I click OK. Guess what? The message window appears. Didn't I tell you, by the time that I'm moving my mouse, I'm generating tons of messages. I have a proof for you. If I move my mouse over here, nothing is happening. Move my mouse over here, nothing is happening. Move it over here, nothing is going on. I even click. You see what's going on? There's a cursor blinks. For each blink, I get a message.